Welcome to Dr. Tarazi's math site.
Hello and welcome. Here is what you need to know before we get to the algorithms.
What is a spanning tree?
A spanning tree of a graph G is a subgraph of G containing every vertex of G and is a tree.
Proposition 1.
Every connected graph has a spanning tree.
Proposition 2.
Any spanning tree will have n-1 edges where n is the number of vertices in the graph.
Proposition 3.
Any connected graph with n vertices and n-1 edges is a tree.
Example 1.
Find all spanning trees for the graph by removing edges in simple circuits. Now, this one is not a tree, okay? It has a circuit here. So we can remove this edge or this edge or this edge to get a spanning tree. See, this is one option. Removing FD, removing CD, and removing FC.
What is a weighted graph?
A graph whose edges have weights is called a weighted graph.
What is a minimum spanning tree?
A minimum spanning tree is a spanning tree for which the sum of the weights of all the edges is minimum.
Proposition 4.
Let C be a circuit in a connected and directed graph G, and let E be the heaviest edge in C. Then E is not in any minimum spanning tree of G.
Example 2.
Find all minimum spanning trees for the graph by removing edges of highest weights in simple circuits. Here, if you look at this graph, this is a simple circuit here. 9 is the heaviest edge, so it can't be in any minimum spanning tree. Same thing goes for 8. See this 8 here? So let's see how we can do that. We remove a B, okay? Now I can remove the 8 here, EC. Now here you have options of removing ED or DC. So you have two different answers.
Example 3.
Find all minimum spanning trees for the graph by removing edges of highest weights in simple circuits. Okay, let's see how we can do that. Every time you see this picture here, you may pause the video and do the problem yourself and come back and check your answer. So, first of all, I noticed this 8 here. This could, because we have the circuit here, this cannot be in any minimum spanning tree, so I removed this FH. Now, don't look at this anymore. Look at this here. Now you can remove the 7 here, so the BF. Now you can remove the 6. Now here, you can remove the 5. See, it here, 5. Okay, now here, this here, you can remove the 4. Now this is a circuit here. You can remove the 4, but let's wait on that a bit here. Let's remove this 3 here. Okay, see like that here? 3 cannot be in any minimum spanning tree. So now you have an option of removing this, BC, or removing HI. So you have two different answers. This is one, and this is one. Okay? And we will do this example now using the algorithms down the road.
Notes.
Finding spanning trees by removing edges from simple circuits is inefficient because it requires that simple circuits be identified. Kruskal and Prim's algorithm successfully built up a spanning tree by adding edges.
Kruskal's algorithm.
Choose any edge with minimum weight and put it into the spanning tree. Successively add edges with minimum weight that do not form a simple circuit with those edges already chosen. Stop after n-1 edges have been selected.
Example 4.
Apply Kruskal's algorithm to the graph. Okay, so we have this graph here. We need to apply Kruskal's algorithm. So we take all the ones, provided they don't make a circuit. You have 5 vertices, so you need 4 edges. This one here, this one here. I'm done with ones. Twos now, you can take this here or this here. BE, EC, this is easy. The total is 6, so that is your answer.
Example 5.
Apply Kruskal's algorithm to the graph. Now, the same thing here. We have 5 vertices. We need 4 edges. Take the ones. This is 1. You can take this one now if you want, or you take this one here. I took maybe this one here. Okay, CD. And then I take this one here. And now 2. You can't take this 2 because it closes that. Okay? So you have to take this 2. So you're forced to have this. This will have only one possible answer. Okay?
Example 6.
Use Kruskal's algorithm to find all minimum spanning trees for the graph. Let's look at this graph here. And so again, here you have 1, 2, 3. You have 9 vertices, so you need 8 edges. Okay? So these are your choice, the edge and the weight. So we have to take the 1 first. I have only this, so I took DE. Now the 2s, I can take this 2 here. Okay? I take this 2 here. I can take this 2 here. Okay? I'm done with the 2s. 3s now. See, I can't take this, all right, because it closes that. So I can take this 3. AD. I can take this 3. BD. I can take this 3. Okay, no more 3s because this closes this. No more 3s, so 4 now. So you can't take this 4 because it closes this. You can take this 4. Let's go back here again. You can take this 4 or this 4. That's why you will have more than one possible answer. So here I took this here, and that's 8. So that complete the thin. So obviously you have 2 possible answers to this questions. 20. You have this answer or this answer.
Example 7.
Use Kruskal's algorithm to find all minimum spanning trees for the graph. Okay, so here you have 12 vertices. You need 11 edges. Start with the ones. This is 1, 1, 1. 2s now. 2, 2. EI 2. I'm done with the 2s. 3s now. 3. AE. HL. BC. BC. KL. BC. K. Oh, now. I'm done with the 3s. It looks like it. There's no more 3 we can do. This 3 I can't do, right? Because it closes this. This 3 you can't take because it closes this. So I'm now going to choose the 4. So I took this option here. Total 25. Now, if you solve this problem, most likely you might not get this because this graph has 12 different minimum spanning trees. But your answer should be one of these. One of these. Very interesting.
Example 8.
Use Kruskal's algorithm to find a minimum spanning tree for the graph. Now, this one is a little bit more kind of interesting. So again, the same concept, but here you have 16 vertices, so we need 15 edges. Okay, start with the ones. This is here, 1, 1, 1, 1, 1, okay? I'm done with the ones. 2s now, there's a whole bunch of ways, okay? You can take this 2, you can take this 2, you can take this 2. Here I took this 2, and then I took this 2, and then I took this 2. Here you can't take this anymore because it closes the circuit. I took this 2, this 2, this 2, 2. I'm done with the 2s here, so I go to 3, 3, 3, 3. That's 15 done, 28 of them. So I get this minimum spanning tree. So this graph, that's a minimum spanning tree. Now
Prim's
we did,
algorithm.
so back here. Okay, so we will see later that this will have more than this correct answer, okay?
Prim's algorithm.
Prim's algorithm choose any edge with minimum weight and put it into the spanning tree. Like the same we did before. That's one of them now. Now successively add to the tree edges of minimum weight that are incident to a vertex. I mean connected to a vertex already in the tree, never forming a simple circuit. Stop when n-1 edges have been added.
Example 9.
Apply Prim's algorithm to the graph starting with A. So start with A. So I have to take this one for sure. Now, I can't take this one, okay? I have to take something connected to these points here. So I have the 2 and the 3 and the 3 that I have to take the 2. Now, from here, you have 3, 3. You can't take this 3. Obviously, it closes this. You have to take this 2. Now, from here, you can't take this. You have to take this one. So obviously here, you have only one possible answer, which is this one, which we found before, okay?
Example 10.
Apply Prim's algorithm to the graph starting with A. Okay, started. Now you take one, you can take this or you can take this, it doesn't matter. Now you have to take this one actually, because connected. From here you can't take this. This is 4, it doesn't work, this is 3. So you have to take the 2 here. You have to take this 2. And now at this point you have to take the 1. It's done. The same answer we did before.
Example 11.
Apply Prim's algorithm to the graph starting with A. Okay, start with A. 9 vertices, 8 edges, started with A. Now, before you do that here, from A you have to 4 or 3. Actually, you can start with any point because all these points have to be on the spanning tree. So we start with A. You have an option to take 4 or 3. You have to take a minimum of the 2. You can to take the 3. Now you have this point and this point are in my tree. From here you can take 3, 3 or 5. Here you can take 4. So you have to take, and you have 1 here. So this is a must. You have to take this one now. Now you reach this, you have this point and this point and this point. You see that you have to take the 2. You reach to this point here, you have to take this 2. Now, here's 4, here's 3. You can't take this 3 because it closes that. So you have to take this 3, that's a must. Okay, now, from here you have 4, from here you have 4. You can't take this 4 actually because it closes this. So you can take this 4 and continue, or you can take this 4 and continue. That's why you will have 2 options. So I took this 4. Now you get this point, you have to take this 3 and this 2 and 8 edges done, and the total is 20, and you get the answer. Actually,
Example 12.
back here, actually you can have this, or you have another answer when you take this instead of this, okay?
Example 12.
Apply Prim's algorithm to the graph starting with A. 12 vertices, we need 11 edges. Okay, 1 is for obligatory, is a must. Now you have option between 3, 2, and 3. You have to take the 2. Now here you have 3, you have a 3 here, you have 3 here. That's why you will have more than one possible option. Okay, so if I took AE, then I have to take this 2 because now this is the shortest. Okay, the minimum weight here. Then when you reach this point, you have to take the 1. 3 here, you can take this 3 or this 3. Get to this point, you have to take the 2 because here you have options. Choose between 2 and 3. 2 is smaller than 3. you take the 2. And then I took CG3. Then you have to take the 1, 4, 3, 11, 25, done. Now, if when you do this problem yourself, most likely you will not get that same answer here, but you should get one of these 12 possible minimum spanning trees.
Example 13.
Apply Prim's algorithm to the graph starting with A. Okay, so start with A. I have to take the 1 for sure. This one or this one, it doesn't matter. So here you have 16 vertices. You need 15 edges. So I took the 1 here. Then you don't add this 2 yet. You have to add the 1 here, okay? Now, from this point, here you have the 2, you have the 3, here you have the 2. So you have many options to add the 2. I took this 2 like that. And then once you get to this point here, you have to take the 1, okay? Before doing any 2s. The 1. Now I took this 2 here. I took this 2 here. I took this 2. Okay, but once you reach this point here, you have the 1. You have to take the 1 here. Stop taking 2s, okay? Stop. You just have to connect it to the vertices already in the tree. So you have to take the 1. This. Don't take the 2. You have to take the 1 again here. Now, you have this point. You can take 3 or 2. Here you can take 3 or 2. You can have options between taking this 2 or this 2. Or this 2. Okay? Or this 2. If you don't take this, you take this. 2. 2. 3 is now. I took this 3. Took this 3. 3. Total 28. So I solved this problem and total 28. Here's the minimum spanning tree. It looks different than the one we had before. And again, you may have more than one possible answer. These are 2 different minimum spanning tree of the same graph. There are more than these 2.
Final note.
When Kruskal or Prim's algorithm is applied to a graph in which some edges have the same weights, more than one output minimum spanning tree can occur. To get a unique output, the edges are numbered in an array, and those having the same weight are added in the order they appear in the array. Thank you, and see you soon.
Thank you for watching. More videos to come. Please subscribe.